this is one of the interesting polynomial rational integrals. So a polynomial rational integral is an integral where you have a rational expression of polynomials. Oh, that's very obvious. Okay, I didn't really add anything to you by saying this. Here I have x squared. Here I have x squared. There are two ways to proceed with this. You could use a polynomial long division. If you remember how we did that. So you would say how many x squared goes into the side of 2x squared, and the answer is 2. Then you multiply both of these, so you get you take away this amount. So we've taken away twice of x squared, and then you take away 2. Yeah. So this cancels out, but then you have a minus of a minus, so you get 4. But then you can't really do anything. So it's 2, and the remainder is equal to 4. So you can write, okay, this is 2 plus 4 over x squared minus 1. And there's also another way to do it if you don't like, polynomial long division, which is the following. Both of them lead to the same, result. All roads lead to Rome. So I factor the numerator, I get 2. And I have x squared plus 1 divided by x squared minus 1. And then it would be so nice. It would be just amazing if I had here a minus 1 and then it cancels out. It would be so nice, right? But can I do that? Well, kind of. So I can just write x squared minus 1. Okay, maybe it just should be in green. But then I add 2. Because when I do minus 1 plus 2, I get positive 1. Then it is fine. And as you might see or might notice, this will cancel out. So we would get 2 times the fraction that cancels out, which is 1, which is 2, and 2 times 2 over x squared minus 1. So 4 over x squared minus 1. So you can really just do whatever way you like. Let's say you don't like polynomial long division. You have something personal against polynomial long division. So you don't use it. And I just don't. So use this. So I've supplied you with 2 ways you could approach this problem. I think that's good. I think it's productive. These are different perspectives. They are important, of course. Why am I drawing a random box? It's because of this. So I want to isolate it from everything else. So that's something. I still need to work with this, like if I integrate this, I get, an integral of 2, because the integration distributes. But then I still need to integrate 4 over x squared minus 1. Now I'm writing this very hand-wavingly, because I don't want to write the integral just yet. I'm just giving you a perspective. So if I want to integrate this, it's not an obvious antiderivative. It's not a multiplication of 2 functions such that I can do, let's say, integration by substitution or integration by parts or anything like this. So I'm stuck. I don't know what to do. But then I kind of do. So just to emphasize what I mean when I say that I still need to deal with this, I will actually write down the integral. You know what? I'll just write it down. So this is our I. It's in this case, if star is true, and it is true, then we would get two integrals, right? We get integral from 0 to half of 2 dx plus an integral from 0 to half of 4 over x squared minus 1 dx. So this is precisely what I mean when I say that we still need to deal with this thing. Maybe I'll write it like this because I have enough space, or maybe so that I have enough space. It's a bit more accurate. So I still need to deal with this. Maybe I'll call it, I don't know, I1. So I is equal to I plus I1. And this is my I1. So that's not too bad. And I still need to evaluate this, of course. So I'm a bit stuck. And the idea here is to notice. What do we notice? We notice the following. Maybe here I'll use the blue color because I have not used it so far. Maybe I can do something with this expression. On top it is 4, there's nothing I can do. But on the bottom, there should be something. Can you try to give it a good look and see if you can make something out of this? I'm looking at you. Why haven't you tried? You need to try. Come on. If you've tried, I'm sorry. I'm not talking to you. Well, here's what I mean. So this is x squared minus 1. So it's x squared minus 1 squared, which is just a difference of squares. I can just write it as 1, x minus 1, x plus 1. You can, of course, verify that if you expand this, you'll get this expression. But if you see it often enough, you know, x squared minus 1 type of expressions, or x squared minus 4, or x squared minus 9, and so on and so forth, you know, it's immediately you see that you have a difference of 2 squares. And you will get used to this. But then this is not nice. Still, I need to... It would be so nice if there was just, you know, a way to separate this into 2 fractions, you know. Where one you have x minus 1, and one you have x plus 1. It would be so amazing, you know. Just splendid, wonderful, fantastic. Is there a way? And there is one. And this way is called partial fractions. So you would get, let's say, a constant here and a constant there. Now, we do not discuss why partial fractions work, because this is not the focus of this tutorial. But what we do here is, if I want to find A, then I plug in the value that make the problematic value, which is in this case 1, makes it 0, into the other two, into the rest of the fraction. So for example, maybe I'll make this more, so I'll write this down explicitly. So A is plugging the problematic value, so in this case the problematic value is 1, but you would plug it into the rest of the fraction. So you would do like this, you would get 1 plus 1 over 4. So this will be 4 over 2. So sorry, 4 over 1 plus 1. This will be 4 over 2 will be 2. So with full confidence, I can say this is going to be 2. Now, maybe it is a good exercise for you to pause the video. Please pause the video and try to find b in the same manner. So we would take the same big expression. B is the one on top of x plus 1, so I need to take the x plus 1. Find the problematic point, it's minus 1, because it gives us a 0. And I plug it in here. I get minus 1 instead of x, and then minus 1. So this gives me 4 over and minus 2. Maybe I should write this as 4 over minus 2 is just minus 2. So this is how we proceed. Then that is just amazing, because I get 2 over x minus 1 plus, minus 2 over x plus 1. Then my I1 is equal to, not the integral of this thing, well, this fraction on here is equal to, it's equal to the other two fractions, so these ones. So if I color this in blue, then it is obvious that if I make this substitution, it works. Maybe I will even write these as two different integrals. But please do not forget your dx's. And this should be easy to work out. Maybe I'll even verify that this is true. It is. It is, that's good. I'm happy. I don't have to reshoot this video. So this is true. And we need to find the derivative. Maybe I will isolate the coefficients. Okay, both of them have a 2. Maybe I'll just put the 2 right outside. And you need to take a moment to think about the derivative of 1 over x plus 1 or the derivative of 1 over x minus 1. So the derivative of what gives us this? And the answer here is the ln function. The derivative of ln of x is 1 over x. That is a good note for you to write. And so if this is true, yeah, I have a little bit more space, I'm happy. Then I can just write. Now notice that we're not dealing with 1 over x. Now if this is true, then if I just plug in x plus 1, it works. Because the derivative of x plus 1, which I need to account for when I use the chain rule, is just 1. So again, the focus of this tutorial is not the integration. So I will not focus too much on it. I'll just hand wave it as I just did. So that the values we get are ln of x minus 1 minus ln of x plus 1. Twice of this, of course. And let's not forget our integration boundaries, which we still need to plug in from 0 to half. Now you can use a calculator for this, or you can just plug in the values. But you need to be careful because think I anticipate a certain problem. Yes, here's the problem. The problem would be that if you plug in the half and you plug in the 0, you would get an ln of a negative number. That could be a bit problematic. We know that the derivative of ln of x is 1 over x, but if you want to integrate this term, you get the absolute value of x minus 1. Now again, the integral itself is not the focus of this tutorial. And so we just give it out now, and then if we plug in the values, we get twice of ln of half minus 1, that is minus half. The absolute value is just a half, minus ln of half plus 1, which is 3 over 2. So that is the first term. You plug in half. Then you take away the part where you plug in 0. So you would get ln of 1 in the absolute value. So 0 minus 1 is 1. And here you would get also ln of 1. Now ln of 1 is 0. So that is out of the way. And I want you to be careful, because what we've just computed is twice of ln of half minus ln of 3 over 2. And now there's a certain property with the ln, and that is you can actually, if you have a difference of ln's, you can write it as a fraction. So ln of half minus ln of 3 over 2. Now don't forget that we're actually still multiplying by 2 on the outside. So I'm not forgetting this, I'm just writing this on the side. This will be equal to ln of half divided by 3 over 2, because this is the positive term, this is the negative term. And then if I divide this by 3 over 2, I'm multiplying by 2 over 3. Then this will be ln of 1 over 3. But then don't forget that we're multiplying by 2. And here I can do something that's a bit special. Or should I not do that? Let me see. Yeah, this looks perfect. This looks perfect. Well, almost, right? Because we still need to work out the value of this thing, which I've left some space for, luckily. So if we integrate 2, 2 is just a constant, so we're just integrating 1. So we get 2, and then you have x. You need to plug in x from 0 to half. So this will give you, one time you will plug in half, and one time you will plug in 0, and you will take them away. Half minus 0 is just half, and 2 times half is just 1. You get 1 plus I1. But we're still computing the value of I1 here. It's saying that the value of I1 is ln of 1 over 3 plus 2. But that's fine. And why is that? It's because even if it's not in the answers at all, not even remotely, you could just make a small adjustment to bring it into a nicer format. And that is, so 1 over 3 is ln of 3 to the minus 1. And with the ln function, it has this special property that the exponent can go outside as a coefficient. So if we write this as 3, ln of 3, we multiply by 2 as normal, as we should, and we bring out the minus 1, then this becomes a negative. So you get minus 1 times 2 times ln of 3, which is just 1 minus twice of the ln function as the answer to the exercise. So it's a bit of an interesting exercise. Maybe, at least from my side, I should have given myself a little bit more space. I mean, as always. The first thing you need to do is you need to look at the expression and simplify it. You have x squareds and x squareds. You can proceed with whichever way you like. And then you simplify your task to dealing with this integral. To deal with this integral, you first need to make the nice observation, and then after making the nice observation, you would proceed with partial fractions. We've also covered how you would do that. So this is the way to proceed with partial fractions. This is called the cover-up method, because you cover up the part which you want to find the, you could say, the coefficient of. So if we cover x minus 1 and we plug in 1, we get our 4, and this is 2. And by the way, it's a good exercise to multiply this by x. So multiply this by x plus 1, this by x plus 1, and do the same thing here, multiply by x minus 1 and then x minus 1, and verify that in the end you'll get 4. Because if the numerator matches, then the denominator should match. So that would be a good exercise for you as well, if you're not sure as to why this actually works. As I said, we're not going to cover why it works here in the tutorial, but this is also a good check to carry out. And then after carrying out the partial fractions, the integrals for these two functions is the absolute ln. One might make the mistake of not taking the absolute value, which I was going to make, but I didn't. So you need to be careful. And then you simplify, plug in, you get this. You simplify a little bit more, and then you're able to reach your final solution.